I know. The two bodies.
Everybody?
Southern Illinois University. They really? Whatever it's called. Is that mortician? That, like,
yeah, it's mortician.
I used to teach that.
Dude, I have one of those. They put like 4 bodies into a hole and light our head.
I'm gonna go grab some headphones. Hang on a second, okay?
I don't feel comfortable here.
Well, they buried it and then they wanted to see like the back, the elevation change. Micro elevation. The bodies decomposing. It was cool.
Body crimes and
Yeah.
I'm gonna need to switch labs. I'll be here with that.
that sort of necromancy.
Yeah.
I'll join you.
Screen sharing, happy.
Like I don't do like scary movies, like none of that.
You're logged into your VT, right? Or
Yeah.
you're not?
Yeah.
Okay. Cool. Forward you my slides. Do you have email?
Wait, so is Slack not enough?
Email?
Yeah.
Like,
Yeah, what is this?
I don't know where I heard that from, but that's like my favorite joke. Do you have email?
Dude, if they said electronic mail, that'd be even better.
Yeah.
have you heard of this
No,
electronic mail? Electric mail?
Electric.
All right.
Oh, yeah.
Got a new laptop and the audio is super low.
Strange.
We can talk like this.
There you go.
I can't hear you.
That might work. Let's try that.
Somebody say something.
Hello?
Test.
All right. It's a little bit low, but I think we can get by. How's everybody doing today?
It's going.
All right, tired.
Alive.
Healthy.
Class is going okay? How are things winding up over there for that? I mean, you guys are getting pretty close to Thanksgiving break, right?
Yeah.
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 Things are starting to get a little more intense here.
Yeah.
Everything's kind of bunching up towards the end of the semester.
Get cold.
Yeah, it's cold.
Yeah.
Cold.
It's hot. It's hot today. It's 51.
Yeah.
Sam's got it right. It's been like under 20 most of the week this week.
Yeah,
Here.
yeah.
All right. Everybody presenting today?
Yeah.
Yeah.
Just us.
I like how every week I'm not in the frame.
You can
bad.
just say,
Can
Can't
we
wait for
sit
the town. I mean,
We are about equity here.
yeah.
It's a boardroom, and then
Well, y'all
you
already
said
had your spot.
EEO.
Well, yeah, because it's first come, first serve in the seating arena.
Empowering women in
Okay, but
geography.
even when I sat over there, I was still out of frame.
First come, first serve,
well,
man.
you sit too far back.
No, I wasn't even sitting that far back. Whatever. Who's going first?
I'll go first.
Well, obviously, unless you know want to go first. I think I'll probably go first. Okay. It don't matter. Sorry, though.
All right.
I expect somebody else.
It's not make sense.
Molly said she couldn't make it.
I just saw her.
She has something at 11.
Slacker.
We should walk out there and go, oh.
All right. You guys still hear me?
Yeah, we hear you.
Yep.
Okay. Now I got my headphones. All right. Perfect. All right. So sharing the screen now. You guys got that one?
Yep.
Yep.
Okay, official start here. It's November 15th, Lab Report Day. A couple of quick announcements. Some of the work that we're doing in the lab and some of the stuff that we've done in the past may fit well with this. So I've never really been involved in this conference at all, but this is ISCRAM, and it is going to be held at Blacksburg in May of 2020. So this is a pretty good opportunity. I may talk to, certainly the work that Sam and Jim are doing might fit in well with this. So there might be an opportunity for us, the three of us, and maybe anybody who else might want to be in on this could cobble something together. And this would probably be something along the lines of one of these work in progress papers, the deadline of which would be January 28th. So this is a 3,000 to 6,000 word submission. It would almost certainly tend towards the lower end of that. These are peer reviewed, so it's unlike, so AAG is non-peer reviewed. You basically submit your abstract and everything gets accepted. It's just kind of a question of which session it goes into. Other conferences though have peer review as part of the acceptance process, and there are sort of varying degrees of that. So I don't know whether this is going to be something I want to do or not, but I'll give it some thought over the next week. There's another similar conference. This is probably more appropriate for one of my former graduate students, but just to kind of keep people aware of what kind of conferences are going on when. This is a risk management model conference in Berlin in May around the same time. So one of the projects, the little side projects that I had this week was working with Charlie on looking at some of his photogrammetric scans of the Strubles Creek area. When he had his committee meeting, we looked at the outputs and it looked as if the DTM that he was getting had what's called curl in it. So this is when you fly your drone, you image an area, and the edges of your area are either bowed up or bowed down, depending on how the camera works. And the reason this happens is because the camera is trying to estimate its position, partly from the GPS, but partly from what it sees in the image. And if the camera is not calibrated correctly for the software, then it has a hard time matching that. And so there's a tension in the resulting model, and it solves that tension by trying to curl the space. It has no idea what's ground, so it doesn't know what it's doing. And so this is an example of what happened. He was using Agisoft to do that. So this is a top view. As you pan down, this is a riverbed, so that kind of concavity is normal. But what's not normal is when you look at that sort of curl happening on the side. So as you move, this is normal curl, right, representing the shape of the riverbed, but this is not, right? So that view of it on the side where it's kind of bowing down is not. So that was kind of an interesting one. He ran his stuff through Agisoft, and we talked about that. He's going to rerun it again and try to find out which camera settings are having a problem with that. I used Pix4D to run the same data and got the curl to drop out, so we know it's not, any kind of an imaging problem. It's purely software side stuff. The next thing that I wanted to talk to him about was using density as part of the model that he's doing. This is kind of an interesting one. So he flew over this vegetated area, and they ideally want to be able to predict stream flow based on the photogrammetric model and the LiDAR data that they've been collecting. So they're using things like terrain roughness. So Jim and Sam have seen roughness calculations. All right, so he wants to use something like that as a means to see if that's changing flow patterns. But because DSMs are so messy, I'm a little concerned, and even DTMs, especially DTMs coming from photogrammetric sources, are messy. I'm not sure that the roughness is going to work. I think that might be a noisy data source. So that density might work out okay. So this is an example of using LazTools, the LazGrid function of that, to calculate point density at every square meter within the scan. Some of these go up as high as 8,000 points per square meter, which is cool. The question was whether or not the vegetation patterns that exist. I'm going to start so this is the orthophoto that came out of the Pix4D scan. So you can see sort of differences in vegetation along the bed. The question is, do those vegetation differences show up in the point cloud? And I think the answer is sort of. If you look at this road, you can sort of see some traces of that as we rotate around. I don't know if maybe the angle's not going to be good. You can kind of make out the road in the density output, so you know it's doing something, but you'll also notice for sure that there is, you see these sort of striped patterns that are coming in here. So that's just pure artifacting from the data processing. So that's obviously not real. So the question is whether or not that artifacting is going to swamp any actual difference that's showing up in density in the vegetation. So I think he's going to run some tests and sort of see if this is going to pan out. I think after looking at it, I think probably not. And I think probably LiDAR is going to be the only thing that's going to work, but it's worth a look. this is just some information on using LazGrid. So LazTools is really powerful. LazGrid is one of my favorite tools in that toolbox because it can very quickly generate orthophoto-like things. It can generate DTMs and DSMs. It can generate these point density measures. It can it can colorify things and apply color maps. So it's pretty powerful tool. So if you haven't used that with LAS tools, you should take a look. And then the other big thing was working with Jim last week on curvature. So Jim, I expect you probably got some things to present on that too.
Yeah, sorta. I tried.
That's fine. So I'd worked with curvature a while ago. So curvature is one of those kind of common terrain-based metrics that you can calculate. You know, at the graduate level, at the undergraduate level, it's sufficient to just kind of use the tools that are around. At the graduate level, you need to look a little bit more closely to see how the tools work. And so in this case, I wanted to dig in a little bit. There's a couple of different kinds of curvature, profile and plan curvature, two common things that Esri will spit out in addition to sort of the regular curvature calculation. And Jim brought my attention to the documentation surrounding micro DEM, which I'll talk about here in just a second. I had programmed this a while ago in MATLAB, and so I had code to do this kind of laying around and had been interested in transcribing that into Python for quite a while. But one of the things I noticed as we were doing is that essentially what it's doing is it's trying to fit this quadratic surface in a 3x3 neighborhood where Z1 is kind of the northwest pixel, Z2 is the north pixel, and so on. In the micro DEM documentation, they just use this, but actually this is kind of standard. So 1, 2, 3, 4, 5, 6, 7, 8, 9, kind of tiling in like you're reading a book, left to right, top to bottom. You use that to essentially, these are sort of fleshed out formulas for essentially deriving the parameters in this equation. But if you look closely, these are actually not the same. So there are some slight differences here in how these parameters are calculated. So for instance, D, according to the micro DEM model, which comes from this amazing dissertation by Wood in 1996. She's actually drawing from a paper on Evans, so it's also kind of important to track through the lineage of some of these ideas. This is the equation for part D of that formula, essentially, and that's different than what's going on up here. So the long and the short of it is the formulas for doing these calculations. This is the calculation for curvature for Esri. Where did it go? I don't know if I have it listed on this page. I may have it listed on another one, but this is essentially the same cross curvature is this -20 times the average spacing times B times D squared and so on. This equation is not that equation, right? And these parameters are not those parameters. So there are some interesting differences in how these things are calculated. So I put both of these ways of calculating this into NeilPy. So NeilPy has been updated to 2.13. One of the things about this, though, is that the magnitudes of this, so there are these values in the front here that, so the -200, 200, -2, -2 over here. Same kinds of things going on over here. These are changing the magnitude of the curvature value. So a slope value is real, right? There's 10 degrees and 20 degrees. These curvature values, you can't pay attention to the magnitudes, right? If you try to build a model that says, you know, above a curvature value of 1.7, that's not going to translate from one method of calculating curvature to another. So if you're going to use something like that, you have to be very specific about how the curvature calculations work. Really critically, though, the direction of these things actually changes. And I've got an example of that here in just a second. So what a positive curvature represents on the Evans-based calculations is different than the Esri-based calculations. So they're exactly the opposite. This is an example of how you'd use NeilPy to do those calculations. You just call this thing that I'm calling Esri curvature. I actually have another function called just curvature, which I'll talk about here in a second, and then Evans curvature. So there's a couple of different implementations. And what plan curvature does, and Jim talked about this last week, is just highlight the the ridges and valleys in your data set. So that could be important, for instance, Colleen, in like a least cost path model that explicitly considers whether you're traveling through valleys or you're traveling along ridge lines. And many paths actually prefer ridges to valleys. Valleys tend to accumulate these rough bottoms, and so they don't work out very well. So, so this kind of stuff can come in handy for maybe a lot of people's work. Aileen Buckley is the lead cartographer for Esri. I know her pretty well at this point. So if you guys are ever interested in talking to her, let me know. She wrote, she's the lead author on one of the big textbooks that's being used now, Map Use, Reading Analysis, and Interpretation. I don't know if anybody has used that one in any of their GIS classes. It's a book that's like 2 inches thick. Sam, were they using that one in maps and mapping at NIU when you were there?
No. We had, I don't even know if we had a book, but all the books that they did use were like super out of date, like ArcGIS 0.8.
Ah.
0.8.
Yeah, 0.8. It was
0.8. Oh, that's really out of date.
It's just a paper.
Yeah.
It's like Jack's prototypes. Yeah, so Aileen is really she's big in the industry. Everybody knows Aileen, and one of the things that I try to emphasize with you guys is how much this all of this sort of endeavor is driven by people, by individuals, and so it's really kind of cool to get to know a lot of the people that are behind a lot of these articles. All right, these are actually just screen grabs of the profile view of these curvature rasters. So I kind of liked the way they showed up. You'll notice maybe some artifacting kind of drifting through the center of this, which is not uncommon in a DEM. But this is a regular curvature calculation. I know the color map is really dark here, but I like how it turns out here in the next one, which is this one. So this is plan curvature, and you can really see the difference between the normal regular curvature and plan curvature, which is bringing out these ridges and valleys, and then profile curvature, which is bringing out these. It's essentially measuring the curvature of whether that hill bends in or out. So this is kind of the hill bending out, and the dark spots are the hill bending in. So this is a combination of both of those two. So move on. All right, this is an example of the plan curvature that Esri calculates. I was going to make a little video here, but I didn't. These are your kind of ridge lines, and so these are the essentially like little valleys kind of on the side of the hill slope from erosion, right? So this is the Esri version of that. If you calculate plan curvature, this is the micro DEM version. And what I want you to see here is that the micro DEM is ranging from about 0.4 to negative 0.4. The Esri one is ranging from 0.26 to -3. So the magnitudes are different, but the signs are also different, right? So what's a positive here is a negative there. So for instance, Jack, when you're working on your data, hot spots and low spots coming out of one of those things is going to be entirely dependent on the way that curvature was calculated. So it's important to kind of track that back and sort of figure out exactly what they did. Otherwise, your answer is going to be exactly the opposite. If you just want curvature, this is one right way to do it. So this tiny little function will give you essentially what Esri will give you. I coded up the Esri version and I coded up the Evans version. But if all you need is curvature, this is the right way to do it. So ND image within SciPy just has a Laplacian operator that you can use to do the calculation, and that happens practically instantaneously and with the lowest memory footprint that you could need. I wrote two different implementations of this. So in the top here, and I just tested it on a random raster of 1,000 by 1,000 pixels. This is a calculation. So as you're developing algorithms to work on this stuff, making it work is kind of step one. Making sure it's producing the right output is step two. So I was constantly going back and forth and taking a close look at between an Esri output, the micro DEM output, and my own output, and making sure that the answers are consistent between the two. So you have to make sure that if you're writing a function, you need to be really sure that you're getting the right answer. Otherwise, if your thesis rests on these calculations, they better be right. So you really have to be very attentive to that detail. So I probably spent 8 hours just kind of going back and forth between rasters and just making sure I was getting the answer I thought I did. But then step 3 is performance testing, right? So are you getting an answer as quickly as you could? And that kind of depends on how you implement it. And I wanted to highlight this just so you can see the differences between different kinds of implementation. On the top, this is what's called a vectorized implementation. So here we're processing the data as kind of whole chunks and using NumPy to its greatest advantage. And in that case, the calculation on this 1,000 by 1,000 raster is about half a second. And that's without any real optimization. I could go through and try to improve that a little bit, but a half a second for this is not so bad. If you implement this as an ND image generic filter, which is how I've been talking to Sam and Jim about doing these things, because it's an easy way to develop. That's the beauty of generic filters. You can write these little filters and you don't have to worry about the details of sort of the neighborhood operations. You can kind of offload that, but the price you pay for that is in time. So the Esri calculation implemented as a generic filter takes 21 seconds to operate on the same data. So that's a factor of 40. So it's a big deal. So how you implement these things matters. I'm definitely not saying, Jim and Sam, avoid doing generic filters. That's a good way to get started. And especially for complicated filters, it takes a lot of work to try to figure out how to vectorize some of this stuff. So some of the things I can show you when you get to that point of how this was written, and it's all actually in NeilPy, so you can take a look at it yourself. But this is a good way to start, but just be advised that it's a little bit on the slow side. I put these things up online, so I added to this terrain visualization and processing notebook. So there's a curvature example that I showed earlier, so that's online. I also noticed, and I'd probably done this and forgotten, but as I'm developing Neil, sometimes I can't always remember how I did things a couple of years ago. So this is kind of just a note to myself, but you can install a package that you're developing. So Sam, I don't know if you're to the point where you're working on functions that are going to drop in NeilPy, but if you do pip install dot while you're in that directory, it'll install it. Maybe you've got another trick.
Okay. No, yeah, I haven't done too much package development, so I would read a little bit more about it, but it's interesting.
Yeah. Well, when you get to that point, let me know. This is, okay. Like I said, this is just kind of a note to myself because I'll forget again the next time. And then for Jim, I wrote a little thing that was going to be a function development example. So if you're writing a little function that you're trying to make a calculation on, something new or something you're trying to implement from the literature, you can do that. And I sort of outlined sort of an open operation with Rasterio and a save operation with Rasterio, because if you guys, all of this stuff is actually up online, but you know, if you tried to code based on examples that you see at your Stack Overflow or whatever, or even the documentation, a lot of that stuff can be very bulky, unnecessarily bulky. And so what I try to do in a lot of these examples is strip things down to the kind of the barest. What's the minimum I need to read a raster? What's the minimum that I need to write a raster back out again? So hopefully some of these things will benefit you guys in the future. I wanted to really thank Jim for pointing me in the direction of MicroDEM. The more I got into this stuff, the more I was really impressed with it. So Jim discovered this past week or the week before that?
It was like last Saturday. Like, I guess, yeah, about a week ago.
So this is, so one of the professors at the Naval Academy wrote this, and it's just kind of this C application that he's clearly been writing for the last like 30 years and just sort of like, adds to it as he's gone along. It can calculate basically anything you've ever wanted to calculate on a DEM, it can do. And so things like slope and aspect and curvature that are normal, but things like rugosity or the terrain ruggedness index or openness, which I use kind of a lot. It can do things for like hydrological modeling. Tau DEM tools are integrated. It can do LiDAR, so it's got some functions to import LiDAR data, and you can produce DEMs out of that. Colleen, I just happened to notice that it's got least cost path implementations in here. So the documentation is pretty rough. He spends a lot more time developing this than he does kind of writing it, and that's normal in science, right? everybody only has a certain amount of time. So if you're spending all this time sort of investigating the functions that go in here and then implementing them, there is documentation, but it obviously could be a little bit better. So you have to spend some time kind of going through and figuring that out. But really nice find here. This is just a nice spot to some of the documentation that I found. And Peter Guth himself, in addition to sort of implementing the software, has some really interesting papers. This is kind of an interesting one that I'll probably, if I ever teach, I'm thinking about teaching a terrain analysis course. This paper on what should a bare earth DTM show is a really thoughtful way to it. And when I started working with LiDAR data, I kind of run into a lot of these same issues. So some really cool stuff here. He's got kind of a military bent since he's in the Navy or at the Naval Academy, but lots of neat stuff. For many of us, I think this paper is going to prove to be useful. So this is quantifying terrain fabric in digital elevation models. There are, within sort of this subdiscipline, there's been a lot of ways of trying to figure out how do we extract from a DEM the metrics that are important for a lot of the stuff that we care about. And so using, for instance, curvature to detect landslides is one example, right? But this terrain fabric is kind of an attempt to dig a little bit deeper and to kind of use more complicated metrics. This terrain fabric is likely to be useful for damage assessment. So Sam, I think using this in your work and throwing it against the DSM that comes out of the tornado scans and throwing it against the orthophotos, even treating them as if they're DTMs. It's probably likely to be pretty effective. I haven't looked at it really closely yet, but it's kind of on my to-do list. And then Jim brought these up again last week. I was hoping to have time to present on them, but if you guys have time, White Box Tools is another kind of really nice one. And then Tau DEM, this is really for Charlie, but using a lot of the derivatives that we get out of LiDAR and especially photogrammetric scans are not super useful for hydrology right away. They're too noisy. So this looks like an interesting package to sort of take some of that stuff apart. Goals for this week are to finish the revisions on that manuscript that's been kind of sitting idle for a couple of weeks, get moving again on the RU stuff. I've been kind of, stuff like curvature but has been on my to-do list for 4 years to port this over to Python, and I just haven't gotten around to it. So with Jim working on that, I wanted to try to get that implemented, but I'm going to have to set some of that stuff aside to get moving on some of my own output related stuff. And then there was a call for request for proposals for undergraduate research at Virginia Tech that I'll probably put a proposal in for. The deadline is December 6th. How many of you participated in undergraduate research as undergrads? Yeah. So I found that to be really valuable. I think it helps a lot of people get a sense of what's going on. And so I think at NIU, I had a lot of undergrads that came into the lab. And I think it'd be great to get undergrads involved in NEAL as well. So
It's a great resume builder.
yeah, for sure. Yeah. For those students that are thinking about going to grad school, it's great. And a lot of the undergrads that get involved in this stuff can be, useful on a lot of other projects, right? So like Sam, you're going to be using undergraduates to help you process the chunks of data, right?
Yeah.
Hopefully, maybe.
Hopefully, we'll see. Yeah.
Sometimes the training takes a little extra time, but ideally you can kind of task them with certain kinds of tasks, and they learn from that, and you do too. All right, that's it for me.
So I had a quick question about the, I guess, metrics that you got in regards to the curvature and all that. Are different ways of segmenting ground out from, like for a DEM, will that affect, or are there like better
Totally
ways for getting a certain metric or applying a certain metric to terrain?
Yeah, absolutely. So that's a really good question. So the short answer is definitely. There are also, and I didn't mention this, but Cloud Compare, for instance, has a method of calculating curvature that's all point-based. So you don't grid things out to a DTM first, you run it directly on the point cloud. So that's interesting. But yeah, definitely the kind of algorithms that you're using that feed into these calculations are going to make a huge difference. And the other thing that I didn't mention so much is, let's see. So the way that this is visualized isn't fantastic, but basically the equations for curvature that are coming out of micro-DEM, the Evans and Wood based stuff, they're much smoother. So curvature in particular can really be a noisy operation. Little perturbations in the data, especially stuff coming from photogrammetric or LiDAR data, can really, it's one thing if you're dealing with a 1 kilometer DEM where they're relatively smooth. But if you're dealing with a 1 meter DTM, then all these little things that happen, all you're using is this little tiny sliding 3x3 neighborhood. And so the calculations can really change a lot depending on the output can change a lot depending on which equations you're using. And then to tag onto that, Wood talks about sort of revisiting the idea. Most of these curvature calculations use a 3x3 window, which is obviously pretty small when you're working with LiDAR data. But there's no reason why you can't do these on larger footprints. So a common way around this within GIS is to just use like a smoothing operation on your DEM before you run the calculations. So if you use like a local mean filter, that'll smooth a lot of it out before you run curvature. But there's no reason why you can't apply just kind of a larger footprint size. And so she's got some ways of doing that, and I've got a kind of a good idea of how that could be implemented in Python without too much work. So, in the old days, you used to have to write a C program that was all kind of crappily array based, but Python affords you some extra tools to make it a little bit easier. So I don't think it'll be that hard to implement sort of a larger footprint size thing. Cool. All right, that's it for me. Who's up next?
I am.
You need to share the screen.
Want to see it? No, I'm sharing the screen. You can see that, right?
Yep.
Okay, cool. So, yeah, worked on micro-DEM stuff, curvature, some 3D design, and Association of Geohazard Professionals stuff this week. So my adventures with micro-DEM were drastically different from your experience.
Really?
It was terrible. But I'll get into that in the next slide. But this is kind of like an overview. So like you said, developed by Peter Guth at the USNA. Has capabilities to do all sorts of different things. Supposed to read DEMs, point cloud, shapefiles. I mean, really kind of anything you want to. And it relies on GDAL and Tiger information and indexes, Tiger indexes. So my adventures turned into misadventures pretty quickly. I think it relies too much on Tiger indexes and GDAL. And I tried installing GDAL binaries from OSGeo, and that didn't help it. And then I couldn't even use DEM files from the USGS. So we're gonna have to compare notes on how to get this thing to work.
Yeah.
Because Colleen and I both tried, and it wouldn't work. It crashed quite a few times, just from not being, I guess, I don't know, causing something to go wrong with the computer, and it didn't like it.
Yeah, the Tiger data was pretty weird. I imagine that's probably a setting somewhere. I just hit cancel, so I was always dealing with UTM stuff, and I just didn't load any of the Tiger stuff. But
because like even when so this right here is supposed to be the point cloud in Kentucky that I've been working with, and it's like and I couldn't even visualize the point cloud. It just kept loading for like 30 minutes without the GL. So I don't know what's going on. We'll have to compare and see what's going on.
That sounds good.
So, and a couple, like last week I printed off these like little design, like 5/8 inch game counter thing tray. And I don't have that deep of a box for a board game that I'm playing. And so I decided to design these little these cover things that clip on around the sides of it and come down about 5 millimeters over the top. So it actually works pretty cool. It looks pretty cool. And I added like the name of the game to the top of it, so you kind of know what's going on. But so it's been about 2.5 hours on that designing and stuff, and I've got more comfortable with SketchUp. So who knows?
Had you used SketchUp before?
6 years ago.
Okay.
I took like a class on AutoCAD, and this was one of the assignments with SketchUp. So
So
Very
I've been using SketchUp for a long time. This is good. I think. Can you go back a slide?
Yeah.
So using getting a handle on using some kind of a CAD is gonna wring a lot more value out of the 3D printer. So there's a lot of really good little tutorials on SketchUp. So if you get a chance, Jack, have you done anything with SketchUp or CAD or printed anything out on that front?
Yeah, I made I was also new to SketchUp. Like my last CAD was in 2010 in high school class. But I made that sign out there.
Oh yeah.
Sign in it. Yeah.
Cool. Yeah, very good. Okay, go on.
Yeah.
Oh, you guys see a good opportunity to port. I like SketchUp. I get the feeling that we're kind of nearing the end of that thing's useful life, and that there may be some other good replacements out there. So within the next 3 years, I'd like to kind of switch off to something newer. SketchUp's been around a long time, and now that Trimble owns it, I think.
Yeah.
You had kind of bought it, but now it's in Trimble, and I don't know. Developments on it has kind of been a little bit weak over the last few years. So
I'll use AutoCAD, just straight up AutoCAD.
that would definitely do the job. I'm a little worried that it might be too much on the training side, but I don't know, maybe not.
Yeah, it's got a steep learning curve. So Jupyter Notebook thing again started last Saturday, and made some headway, and then worked on it some this week. I was kind of having trouble finding time on it, but so I started working on it, and I got like this part basically done, and I built a function on how to do profile curvature and stuff like that, and also to take an array and change it into a raster and save it. And then I tried running it on my laptop. It ran all night, didn't do anything. It was 1,000 by 1,000 rastered as well, so I feel like it really shouldn't have been that big of an issue. But then when I tried to run it on here, I let it run for might even over like a couple hours at least, and it didn't. No joy. So talking with Sam, he said it might be just something got hung up and it didn't want to work. Something happened. So he also explained why Jupyter Notebook's a thing, like what I should probably use it for. So I switched over to Spider. So I can like sit there and just write the code and get going on that. And then maybe I'll change over to Jupyter Lab afterwards to explain what I did to myself. And yeah, but so right now what I'm working on is masking the raster to get it down just to like basically right here, like this bottom part right here. And working on retyping the code for the curvature calculation in Spider. So, and then so I started a cemetery mapping project when I was during undergrad, and I got about a third of the cemetery done. But then I stopped because I graduated, and it was actually kind of like an important task to veterans because I was marking which ones were veteran graves and stuff, and it was pretty neat just to see like the history part of it. But I stopped doing that, and then I want to get back into it and try and finish up the mapping part this winter. But part of that involved talking to some people that I worked with to try and it kind of became restarting the project and eventually publishing it, but less on the actual like GPS mapping and more about using near Earth imagery techniques. And so I spent about an hour and a half looking through literature and from through the library website, and there was definitely a gap. A lot of people have been using ground penetrating radar and stuff like that to just image the subsurface, but that's like a very like specified area, and it's really hard to look like, I guess, wholesale. So what I want to do is, and I built some research questions off of that fact, and because a lot of the near Earth imaging techniques have only been used on large scale archaeological projects just to find like, all right, well, here's a building, here's a structure. So what I want, so some research questions that I kind of formulated with, that I'm working on getting to the other people that I've talked to so far, that people that I worked with, is that which, NEAT is, provides the most accurate classification of the surface in the cemetery. So, and ones that I found I could try are near infrared, NDVI, Landsat false color, and LiDAR. And then as an applied research question to that is which technique would be the best for assisting law enforcement in missing persons cases for clandestine burials. So clandestine burial is just like where somebody goes and digs a hole and dumps a body in there because the dirt's turned up. But you know, how do you look at things that are in a cemetery when they're like 50 years old and it's all grassed over or something like that? So it's kind of what I'm starting to mess around with. And then other things that I kind of this week, I've created / going to create a promotional statement directed at student members for Association of Jihad Professionals. I'm on the membership committee for that organization, and we're trying to reach out to people because right now we're like 400 members, I think is what they said. No, there's a lot, but there's not really. There's like 100 something, 200 student members, and they want to grow that. It's mainly composed of manufacturers and contractors and consultants. So met with Corrine this morning about lit review comments that she had. She seemed pretty positive about it, so I don't have to change much, but I gotta have to make some changes. And it's the end of the semester, so a lot of students are emailing me about core regions, and it's overwhelming because I walked 10 minutes across campus and I got like 30 emails about this one assignment. So yeah. And then so high priority, it's gonna be probably Monday, thereabouts, is doing the EMLID benchmark collection. Probably gonna be near Blacksburg Elementary School or something. There's an elementary school off of Glade Road. I think it's Glade Road. Whatever, I'll figure it out. But do it there. Keep working on my lit review for 5014. Present my draft presentation on Tuesday. Homework, obviously, like always homework. I'm gonna try and finish this my Python script for the profile curvature this week, hopefully. But I'm also meeting with Hoagie Wellness on Monday midday or early, or actually morning, about cooking classes for the food insecurity project I'm involved in.
On the profile curvature, I think it's a useful project to learn from. So if you want to put time in there, that's okay with me. If you haven't installed NeilPy yet, teach yourself how to do it with NeilPy.
Okay.
Now that we've got a function in there, we don't want to. Like I said, it's really good for you to learn, so that's definitely time well spent. But
Okay.
Yeah.
Cool. I can do that. And so my internet's been giving me problems on my laptop, and it finally decided to just die. Not my laptop itself, but the internet. And I can't even log on to the internet on campus now. So probably gonna run over to tech support either this afternoon or Monday morning to get some help on that. Maybe it'll take an hour and a half. I really hope it doesn't take an hour and a half, but that's what I'm allotting. And gonna read more articles on remote sensing. But I've collected about like 15 articles the other day that I need to read through and make notes on. So and that's it. So cool.
Okay, thanks.
Okay.
We should do like Granny Shop randomly generate.
Mm-hmm. Can you see this, Dr. Pino?
I can see here.
I'm still seeing Jim's.
Yeah, do the share like the full screen. Screen.
Oh yeah.
Okay, how about now?
Yep, you got it.
Okay. So here's my lab report. First thing I'm going to talk about is my RA stuff is very busy. With this stuff, I finished up data collection. We're doing like some aggregation. I need to read a little bit more about how they do this and how we like kind of weight and normalize the different variables, I guess. I have some writing to finish up for that, and then IRB and survey design. And then I guess Santa Maria had some proposal deadlines coming up, so I did a lot of like reading stuff for that. So then piece of stuff, we did that lit review presentation is just a rough draft, though it definitely needs, there's like, I don't know, I guess we're kind of strapped for time, but it's kind of hard to like jam my 8 pages into that. But yeah, also got my lit review, the paper feedback from Kareen, met with her, and then also Lindsay and Allison sent me their feedback and did a little bit of work on there. And also when I was proofreading the proposals, I found some new sources that I want to include, especially for like the significant section, because that's where they mainly overlap, is like the like actual effects on communities and stuff like that. Then I looked back into the coastal DAM and stuff, how they actually like made it, and some new Mintai stuff, and then some miscellaneous stuff like just updating my lit review notes. Also planning my final project for Dr. Chow's land change modeling class, which I think is going to be might be a little like useful introduction to some stuff, and I'll talk about that in a second. And also animal field of view, kind of unrelated to the Mintai, because it's something I'm thinking about.
Are you gonna present the animal field of view?
Yeah, it's part of this. Yeah.
All right. Great.
So the folks at Mintai sent Dr. Pingle some new demos and stuff on their camera's ability to like show other cars and stuff, other road obstacles, stuff like that, in on a slow moving car about 20 miles an hour. Problem is like half the links they sent just went to 404 errors. So, but they did send a couple cool demo videos, and this is just a screen grab from one where you can see that like the stereoscopic, left and right images from video images, and then this is the depth here, so you can kind of see this car. The depth range isn't super great. I estimated like around 2 or 3 car lengths. Like you can kind of see this car over here. That's just in the corner of the field of view. Like I don't know, maybe that's it. It's kind of hard to tell just visually.
Yeah, I think a lot of the color contrast was being devoted to like near-term stuff, which is interesting. Some of that stuff from the hood of the car is showing up, but what's the rest of the stuff at the top? Just noise, or is that like bugs on the windshield? Or
I think it's noise because it's all sky, and like then there's this noise from the reflection too off the hood of the car.
Yeah.
But yeah, so the range is only a few car lengths, which is fine for like cars driving adjacent lanes, or like stuff that's right next to the car. But like looking ahead where it's going, it's not super great. Like you can cover 3 car lengths in less than a second. And it also, the range seems comparable to like when I was playing around with the Intel RealSense. Maybe like 5 meters or so.
Yeah.
What's their like target for this? Like, why are they making?
So one of their emphases is like object avoidance, and so they had some other videos. Like the first time they talked about this, they put on like a drone, and
Was it that video you showed?
Yeah.
Same company? Okay.
yeah, and that was like their like very shiny demo.
Yeah.
Like this is just like a
More
screen
real.
capture, like
Yeah.
but so yeah, it seems comparable to that, but this got me thinking about something. So they have wide angle lenses so that they can see like in adjacent lanes or sidewalks and stuff like that. And a lot of these computer vision, like the Intel RealSense or Kinect, seem to be really focused on kind of imitating human eyes with our eye orientation and stuff, or like the general like predator, like forward-looking binocular vision. But like vehicles need to see everything around them. So what if we tried something like horse vision? So this is a horse's field of view, where they have this small area of binocular vision. This photo actually is a little cut off, but this triangle right in front of the horse is binocular vision. And then they have these really wide areas of monocular vision that go almost all the way around them. that's one of the reasons why if you ever walk behind a horse, you're supposed to like keep one hand on it so that it like knows where you are. 'Cause that's you get nervous when things are in the blind spot. So like, what if we like? Why don't we make cameras like kind of like the real sensor Mintai, but using some like horse vision. It's like but I like but the term that came to mind, and you can kind of see like. I was reading a little bit about this. They have interesting eyes where their pupils are this wide oval shape so that they can get such a wide field of view. And they also don't need to see what's above them either. And obviously an eyeball is different than a camera. But I don't know, it kind of makes sense. And then I was also thinking with this monocular vision, like you do some like on the fly structure for motion. That might be like pretty computationally taxing, but I think it's a cool idea. Yeah. And I know there's also stuff like I think GoPro has like a 360 action camera, which is cool. I don't think it gets the region of binocular vision, which is nice. But anyways, yeah, this is my little musings on horse computer vision.
Cool.
Right before you go to sitting there. I wonder.
But yeah, actually, I did do this last night. I was like, man.
Shower
I
thoughts.
think Kia or somebody, old teacher has one of their cars, but they have a camera system where you can like I don't know how, but it takes the images from like basically the square around the car, and as you're backing up, it gives you a sense of that side vision as well as the front and back.
Yeah.
So I don't
Yeah,
know.
when we test drove a Nissan Rogue a few years ago, they had that system. It was amazing. Like
That's cool.
it basically constructs like what looks like an aerial photo from all of these side cameras. It's super cool.
Yeah.
So maybe that's what needs to happen. Like I'm like instead of like having just like a 360 ball somewhere, like having it spread out around.
Yeah, and one of the problems is I think partially just our human perception. Like when we get like a really wide angle, like it messes with your spatial cognition because of the distortion and everything. But obviously, like this is just a normal way for a horse to see.
Yeah.
So we need to go back to horse and buggy.
Yeah. Yeah, horses. Yeah, horse and buggies. They automatically
Exactly. They stop the when something.
With that kind of like car, like the multiple camera overhead thing, I saw a video. I was trying to find it like a couple months ago. I couldn't. I think it's from like GMU, George Mason University, where they took like security cameras on a campus and then stitched them together on Google Earth. So like the user could sit there and like drag around and like look. Because like the cameras are high up on buildings, so they could get like this.
It's kind of like
photo thing.
Sometimes they do this in football games. So like change camera views, but they'll like do
Move it
some
around in 3D.
photogrammetry so it looks like the camera's like smoothly moving like across the stadium.
Yeah, I wanna find that. I thought that was kind of cool. But
Oh yeah, it's like you have
Like
like
to get a different angle on like a touchdown or something like that. Yeah.
Yeah, pretty neat.
yeah, or like you see like now they have like somebody like actually like a camera like sitting in the stands or how they like interpolated it so it looks like you're sitting on the stands.
Yeah.
That business idea years ago.
So anyways,
Gosh, it's big and also big.
that's the end of the Mintai stuff. So my land change project plan, I want to implement that multi-epoch structure for motion using the publicly available aerial imagery. For my final project, because it's land change, you give it DEM of difference. And I think, like, this is something I might be able to use, and I've used this. So that's kind of my plan for my final project. See how it works, see if I can get it working and everything like that.
Cool.
Then to the coastal DEM stuff. So last week, kind of reviewed like on paper that wasn't really the focus of like our lab. Which is just talking about the changes in vulnerability predictions and estimates. So this week, the same authors wrote a paper about how they generated it, Culp and Strauss. And so this is about how they actually made it. So the coastal DEM, which is basically just a correction of the shuttle radar topography mission in the coastal areas, which is known to have vertical bias issues, mainly positive vertical bias, so it's thinking that the land is higher than it actually is. And that leads to underestimations of coastal hazard risk. And the vegetation and urban development is mainly what causes that vertical bias, because SRTM is more of a DSM than DEM. So when you have like say 10-meter high trees, it's might get a tree canopy, which is 10 meters above the actual land level.
So
So
on that front, so my impression was is that the radar from SRTM actually penetrates reasonably well through the canopy, and that the problem isn't that you're not seeing the ground. The problem is that you're also seeing the trees.
okay, maybe it's that. So they described it as not showing. They said that it's not exactly a DSM, but it's more like a DSM than a DEM.
Well, it's a similar thing as LiDAR, right? So LiDAR, you're obviously getting a ton of stuff from the canopy or whatever, but you're also getting the ground, but then finding that ground surface is a bit error prone. The urban thing is a little bit different because then you're actually getting reflection off of buildings, right? You're not getting any penetration through the office building that you're imaging.
Yeah.
Okay, sorry, didn't mean to interrupt.
So people have known about this positive vertical bias for a while, and they try to use regression analysis based on things like vegetation height or building height in urban areas. But when you do this, like you can't include too many variables, and it will only work in a certain environment. So like if you want to do it in like this forested area, you can use this regression and it will work pretty well, but you can't apply that to like an urban area. And if you try to use too many variables, you just kind of break it. It doesn't really work out very well. So neural networks provide a potential solution to that because you can include multiple variables, and also like they trained it on LiDAR-based DEMs. And the idea with the neural network was, of course, to like be able to make it a single solution that can be applied in multiple environments. So they used LiDAR DEMs from NOAA and the Australian government as their ground truth training data. And then they tested it in US and Australia. And they also applied it to like all the coastal areas around the world. And some of the other variables they used were slope, population density, some ICESat data, and vegetation data, because those are all also correlated to vertical bias, and past studies and stuff looked into those or like done individual regression. And I think there are a couple other neural networks, but they're like really focused on like a certain area or type of environment. So this figure, you can see the red is the original SRTM, and then the blue is the corrected. So it's pretty consistently much closer to being like zero elevation error. There's like a consistent like 5 to 10 meter positive error in the plain vanilla SRTM, and it's the blue line being like, I forget what they said the blue regions were, but the blue line is pretty good. And it also shows the different effects of like slope density, population density, and canopy, vegetation density, stuff like that. So results. One of the cool things they talked about my hometown, Charleston, South Carolina, is one of the there were like particular areas where they showed how it worked. So this top pane is the LiDAR data, which is considered to be like the ground truth. And then the original SRTM and the adjusted using their neural network solution. So some of the areas they pointed out was this area northeast of Charleston in Berkeley County, which has this like old bridge going across, but it's also heavily forested. So in the original SRTM, you see some pretty serious error here compared to the LiDAR elevation, and it's kind of fixed. It's not perfect, but it's a whole lot better than the plain old SRTM. Another good area to look at is Mount Pleasant. So that's this area right in here, and that's my house. I tried to pick it out, so I couldn't pick it out, but it looks like it's really tall. So this area is very suburban. So there's a lot of buildings and also trees. It's not like as densely urbanized as this area of the peninsula, like downtown Charleston. But it was fixed pretty well. And this area, interestingly, is kind of one of the lower density, like newer suburbs. And it seems to have like the most lingering error. Like it's still fixed, but like you can still, there's a pretty clear visual difference. And then some areas it didn't really have to fix anything, and it did a good job of not doing anything. So the marsh areas between, so these are the Barrier Islands out here, and then this is just marsh and water. I did a pretty good job of leaving those alone because they're pretty much fine the way they are, which makes sense because it's just marsh. Like it's just grass that's maybe a meter tall. But yeah, so it fixed what it needed to do and didn't fix what was not needed. And then Brisbane's a little more difficult to see because it's there's a lot more vertical variation. That's why these areas are gray, because the way they like sorted the coastal areas is that they didn't bother with things that were like above like 30 meters in elevation, because for the purposes of like coastal flooding analysis and stuff, it's not going to flood. So, but yeah, it's a lot steeper, and you can kind of see some of these low-lying areas. The elevation is brought down a little bit, but Charleston is so flat that it's a lot easier to see. And yeah, so that's that. And then my goals for next week, maybe keep working on a lit review. I want to play with some of that Pix4D stuff, trying to get like some simple structure for motion stuff going before I try that like fancy multi-epic stuff. Data aggregation, normalization stuff for RA, and my survey design, RB proposal writing, and also write for our manuscript. So, yep, that's everything I have.
All right. Thanks, Jack.
Alright, so this week I had a flare up with my narcolepsy. I'm very tired. I worked on my lit review stuff and like editing others for about 4 hours. This is just like a breakdown. I read Molly's proposal. I'm still working on Jim's and editing that. I was able to look some more at mine and also create a presentation for it. I still need to finish that up. Like really getting down what I want to say for the draft presentation. This is micro DEM. We talked about a couple times already. I tried. I feel like that's a lot of what I've been saying, but these were the messages that popped up when I tried uploading the USGS DEM, which Jim also got. So I spent about an hour trying to figure this out and like asking Jim about it, and then I had to go to class. So I didn't get to spend too much time with this, but I didn't know how to fix this. So Jim was trying to do the point cloud thing and had to restart it a couple times. I read the innovative technologies used to investigate segments. Oh, this is the other one. Sorry. I read a couple things this week. This one was about comparing Incan roads to the least cost path analysis. And this was written a few years ago, so it's not fully up to date on some of the background information, because the roads are now a World Heritage Site when they weren't at this point. And he found that a lot of them followed the least cost path analysis pretty closely. But there are some areas where it's harder to investigate because the roads have been destroyed either by urbanization or by the Spaniards. Yeah, no, really. So it was interesting to read because he did talk about how he was trying to figure out if least cost path analysis could be used to like determine if the roads were built by Incans versus people before them, like what was already there. And the answer was he could not, but he he did find some really interesting stuff about the paths and stuff, and like how they were pretty close. Forgot which one is which color-wise in that image. So the red is the least cost path, and the blue is the Inca Road for this one. So this was the one that I think followed it the most closely, which is pretty cool.
How did they how did they score followed closely? So when you do these things, you can kind of eyeball it and say, yeah, that looks pretty close. But one of the things that I haven't seen is a quantitative way of expressing how close it is.
Yeah, he did mention at one point that on one of the trails it followed really closely, and that the furthest off it was like a kilometer or something like that, which I thought was still pretty good. But he didn't really, I don't remember him going into too much detail on that. It's a lot more like, there were a lot more images than text.
Okay. As you're going through the literature, keep an eye out for that. It's something that I've been interested for a while, and I've got some ideas on how to actually quantitatively implement this, but it's kind of a common GIS problem. So I feel like there's something that's like outside the domain of least cost paths that's likely to give us the right answer. But at some point, like you can imagine, like what you'd ideally like to do is have like a correlation, right? Like these two paths are correlated 0.97, but the standard correlation doesn't work like that. There's what's called a bidimensional correlation that actually Waldo Tobler developed. That would probably do it, but there's going to be some pre-processing that needs to happen there. So we can talk more about it at the meeting.
What about like a similarity coefficient, for data mining purposes? You could do
So,
like,
I mean,
like Manhattan distance or something like that, or Euclidean distance kind of neighborhood. And
yeah, it's the details of that calculation that are a little bit weird. So if you think about, so obviously some kind of distance metric, but how that actually operates on the data itself, that's a bit of a, you can't just like put these two line segments into stats models and get run a regression on it. Like it's going to be a little trickier. So.
The other thing that I read this week was this innovative technologies used to investigate segments of the Inca Road. You could definitely tell it was an engineering paper. It lacked, I thought it was interesting, but it definitely lacked interdisciplinarity. That this paper was written in 2013, so LiDAR was available at this point in time. But instead, they decided to use photogrammetry techniques, so just taking like the pictures and stitching them together, which I thought was a lot more work than it should have been. Also, the bottom picture kind of cracked me up because it looked like Minecraft.
It
But
might be SketchUp.
Totally SketchUp, yeah.
Yeah, that's one of the like default like
Yeah.
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 so they were just trying to model like what that building on the where's the mouse thing? I cannot. This thing right here. They were son of a gun. They were trying to like model this, and so they. I think this paper could be improved in many different ways, including using archaeologists to like maybe help them with the findings, because from what I could tell, they literally said that we do not have an archaeologist with us in the paper. They obviously also don't have a geographer in the paper. Just based off of all this, they go a lot into the specs of everything that they used, and basically what they ended up finding in the end is that the Inca roads were able to withstand everything for so long because the Incans had a great understanding of the location and like how things were affected by it. and this is the paper that mentioned that some of the roads they were able to do some experiments to tell that some of the roads were older than the Inca Empire.
Hmm.
And that also, there were areas where the roads were destroyed by the Spaniards. So this is the paper that mentioned the Spaniards messing everything up. But I just thought it was weird that they would use like some of their choices I didn't fully understand. But again, I don't think they had a geographer with them because they used the Nikon D90 to do the photogrammetry, and they used ArcGIS Explorer and MapSource. So
What was the last one?
MapSource,
Oh, map source. Okay.
yeah. They also had a sentence at the end of their spatial location and mapping that just didn't make much sense to me. But it was interesting to read about read it from an engineering perspective, but I definitely think it could have used more perspectives.
Classic engineers.
Classic engineers. Like,
Are you saying anything bad about engineers?
it's very technical, and a lot of the paper I've skimmed over because this is a blank thing that does this and this and this and this, and it is. They also, I don't know if they use a Nikon D80 or a Nikon D90 because they mentioned both. So it could use some improvements, but it was good to read.
Cool.
So next week, hopefully Jim and I can figure out micro DEM. We'll find out.
So when you guys install micro DEM, you're immediately getting a GDAL error?
Yeah.
It was after the install and when I tried to open up the DEM from USGS.
Okay. Yeah, that's interesting. The laptop that I had already had GDAL installed, so I wonder if that's why I got a different result.
Maybe. How do you install GDAL?
That's a can of worms, my friend.
Okay.
Yeah.
Great.
The short answer is Conda install GDAL-C Conda Forge, but probably you're going to need to add a path to that install to your system path.
Okay.
So I'll take a look at that today. I've got this laptop that I'm on today has never had. I don't know if I installed GDAL on it or not, but it's never had micro DEM on it, so I can take a look and see what happens.
Okay.
Alright, so add install GDAL to that. Finish or work on editing my literature review. It's not going to be finished editing, it's just gonna get edited. And also look up some more research to fill in some gaps. I want to look more into like settlement patterns in the Amazon, maybe looking more at some modern day stuff and see if that could be of any use, as well as looking up more of Dr. Gregorio de Souza's work, and just seeing what he has to say about the Amazon and if there's anything else that could be of use. Yeah.
All right, sounds good.
Are there scissors?
Yeah.
I'm gonna get a coffee refill while you guys are loading up the next one, okay?
Let's go. Just make it easier. He's going more coffee.
Wait, we're done.
They should do
Yeah, you can just start.
Don't bear.
Dog bears.
Not fair. It's not engineers.
It's just like the last sentence.
Did you see what I sent you on Slack?
Um,
I didn't know what ArcGIS
Oh, so I
Explorer
really
was.
think-
I looked up. It's a mobile app.
Like,
I really
have
think
it.
what you can do
Really?
is if you don't take Z into
Yeah, I
account, just do
remember
X,
that.
Y coordinates, like that similarity, you could do the Euclidean distance and then use
GIS
a
class that was like a scavenger.
either a cosine or a
And like we had to
or
find these things and then put them in the map.
I'd probably go with the cosine.
It's like you
Or
just
is
like
it hard?
Or is that collector?
Because
oh that's
yeah.
collected, that's what it was.
yeah, I'd do one of those
Can we
two
use our VT list?
because it's a similarity coefficient that kind of is really interesting.
It's kind of cool.
The last sentence under spatial location and mapping in this paper is the team could have included engineering calculations, sketches in the GIS program, but due to time constraints, this was not done.
It's also probably not. Whatever.
GIS.
What? That makes no sense to me.
So you can go around and like tag locations.
I think at one point I wrote why
Yeah,
though.
just like drop some points and stuff.
But ArcGIS collector.
Oh, yeah.
You know, open up that open street map, open map kit thing. You need to have like a node that you connect to. Use it. I don't really understand the
A
details.
node?
Okay, man.
Yeah.
Oh, the
Open
um,
map
I
kit.
don't understand what.
Thing that you
oh
can
yeah,
put
download
a place
that.
ago.
yeah.
So
Do you ever use that OpenStreetMap Turbo?
No. What's that?
It's a OpenStreetMap.
Oh yeah, that's right. No, I did not use it.
They definitely needed more people on this thing. Like, this paper has a lot of authors. Like, look at this list. It's because a lot of people went into collect data,
Yeah.
but they, for some reason, decided to leave out an archaeologist.
Yeah.
Why?
Cool. All right. I shall go. It's snappy. Woo, I'm going real too fast. So yeah, keywords, and time is allotted for those said keywords. But yeah, so I was just trying to do some brush up on linear algebra. You know, you can learn anything on Khan Academy. So was looking at just eigenvalues, eigenvectors, and they're just fancy words for not so fancy things. But yeah, just was kind of brushing up on that because it's always good, but there was kind of a reasoning behind that, and that was because I applied for a job at Torque Robotics, which is a local
Ooh.
company here in Blacksburg.
saw that.
Nice.
Well, they do the card.
Yeah, they do the self-driving cars, and they had a geospatial data engineer job available. So I was looking at that and applied for it because that's exciting as crap, you know. So if you've never seen their website, the website's really cool. They've done a whole bunch of transcontinental fully autonomous drives using their LiDAR Lexuses, and I don't know why they bought Lexuses. You could have put that on a Toyota, and it's been just fine. Yeah. But yeah, they use LiDAR, radar, and object detection for photos in regards to their methods, and their videos that they have as propaganda on their website are actually like astonishing. Like you see like people like coming out into the road and they're like stopping immediately, and like even like small things, it won't just like stop the car and like jerk you forward. Like if somebody's just kind of stepping onto the street and stepping back onto the sidewalk, it will kind of veer around the person, but also account for the car next to it. Really cool stuff. But yeah, so there was, after poking around with that, and made friends with the LinkedIn with the CEO of the company.
Basically hired.
Yeah, basically hired. No. Yeah, so he's a former Virginia Tech person that was like a mechanical engineer, and they went to some hackathon thing or whatever with robotics and made self-driving cars, that kind of stuff. So decided to continue it. So yeah, and then this Coursera thing is another kind of MOOC, massive online course. I don't know what the other O stands for. But yeah, this is kind of the, after reading and looking at different specializations, this is offered by the University of Toronto for self-driving car specialization, and that was kind of my idea around it, because they were talking about having a background in linear algebra, as well as other matrices, calculations, and stuff like that. So this specialization or route or career path is very interesting to me in a lot of ways. It's fun, cool. Tell people you work on self-driving cars.
This is really exciting, Hudson. That I've been really hoping to make a better connection with Torque, so I'm happy that you're doing this.
Yeah.
And I second your interest in linear algebra. That's like one of the most powerful skills I think you can add to your programming toolkit. It's just a really efficient way of taking apart data. And
Right.
when you're dealing with this kind of instrumentation, you have to be crazy efficient. And it's amazing how simple little manipulations within linear algebra yield these like great
Right.
results. It's cool.
Yeah.
I still have my linear algebra book with me. If you want me to bring it in?
Sure. I mean, I took a class sophomore year in linear algebra, and I was like, I think I'll read you the
Love that.
textbook. Yeah. But
I can bring it.
that would be cool too. I would appreciate that. Yeah, so the whole basis of the work is kind of the integration of feature manipulation engines for use for piping geospatial data into their other kind of sensor information data, whether that's the IMU associated with the LiDAR and all these kind of different key components working together, object detection, whether that's like OpenCV or something like that. So definitely exciting stuff. And I kind of enrolled in this. They give you like a month free, but it's not a month-long course. So we'll see what happens. I don't know if there's like opportunities in the grad school that like pay for that kind of stuff or not, but we'll see what happens. And then
You need rep right here.
No, GRDP. Look it up.
GRDP.
Yep.
All right, I'll make a note.
Graduate remote desktop.
Yeah, like professional development.
Yeah.
Cool. Anyways, that was fun. That took up a good portion. So there's that and then some other jobs. My brother works at GE, General Electric, and they have like a data technology leadership program that he gave me the referral for, and it's like guarantees somebody looks at your application basically. So yeah, so doing that, it's all hot stuff. But yeah, so other stuff I worked on, working at Unity on this kind of theme object interaction between point cloud. You see before in Unity, I've had point clouds be able to be imported, but that's only just for viewing it in the VR. Ideally, you want to interact with it, do some stuff with it. So I was kind of working on getting a lot of virtual reality toolkits installed, so that a lot of the processes that lead up to being able to use VR are kind of like streamlined. And it's not like I have to build them myself, which would be a tremendous amount of work, but a lot of people have prefabricated interaction techniques and teleportation techniques around a scene idea that I'm trying to get here. So wasn't able to make too much headway on that, but was able to kind of get kind of a base for that, as well as like a project file folder directory in Unity. And then this was a scan that we initially done like a year ago. I don't know if you guys saw it at any point, but I was able to kind of enter the VR capability mode of Poetry. This instance was, I guess, originally built for cardboard, which is kind of outdated, I guess at this point, 2-3 years maybe. But I wasn't able to test this directly on a HMD because I was doing this offsite on the Vive itself, but it should be able to detect VR system and then be able to display in VR, but don't quote me on that yet because I don't know if it works exactly. So, but yeah, that was some time like forking projects and kind of toying with and messing with some of the inner workings of the code and pulling some other APIs and SDKs together to try and do that. So, and there we go. So some goals. Sent out the writing that was on Slack. We appreciate any feedback and you have time. We've gotten a couple feedbacks already, which have been good. So
I know everybody's really busy and here you have your own things, but if you can donate 20 minutes or 30 minutes to Hudson, I'm sure he'll pay it forward.
Trying to do it
Back.
Trying to do it tomorrow.
Yeah. Do you want us to comment onto that drive link you sent
Yeah,
us?
like
or
the
do you want
drive
us to-
link is probably the best comment section because when I downloaded it off the like Google Doc thing, it just like formatting stuff like crap. So
Okay.
I think best way of keeping track of comments and all that kind of stuff is through the Google Doc.
Sounds good.
So yeah, and then I'm gonna continue both the systems that I'm working on with the Unity selection of points as well as teleportation. Yeah, sounds cool. It's stupid. But yeah, and then as well as working on the whole WebVR raycasting and gaze techniques. I see that it might provide some benefit in doing that, but we'll see how that kind of works as far as the gaze thing goes. But yeah, that's everything.
All right, thank you.
All right, I'll send us home.
You got a minute, so I know you have 20 minutes.
I'm taking the full time. So.
Dude.
Um,
Donuts to get
Oh,
to.
buddy.
Get kicked out of the union. Yep.
yeah,
No longer
sorry.
representation.
Yeah.
Keep your
union
dues.
reps here. All right, we'll get started. This is one of those weeks where like I had a bunch of things I wanted to do and then it just kind of disappeared. Like I'm pretty sure my Tuesday, Wednesday, and Thursday just disappeared out of my books. So it wasn't as maybe as productive as I would have liked it to be. I did make some headway on a couple small things, but overall not that productive of a week, I would say. Literature review fun, yeah, it's been tons of fun. I met with Karina and we went over my lit review, and it was pretty good. She said that I just need to kind of smooth out some organization type things. She said working on my presentation would help that, and I feel like it did because I sat around for a while just thinking about how I would organize my presentation and how my lit review should be structured. I still have a lot of work I need to do to get it where I want to be before we submit it for the semester, but I feel a little bit better about it after meeting with her and kind of presenting yesterday. Python framework. So me and Dr. King were working on like doing a quick wiki intro into Python, Anaconda, some useful packages, and a couple other like install things. And then Jim asked me how to set up Jupyter Lab, and I haven't taken notes on how to set it up. So as I'm walking Jim through it, I'm taking notes so I can create a wiki on it. So we can like, I'll have like a wiki on how to set up a Jupyter Lab server, which would be pretty cool. Yeah, I think that's all for the Python stuff. Yeah.
Yeah, I'm glad you mentioned that Python page. I forgot to mention that. So
Yeah.
hopefully that'll come in handy for people moving forward.
Yeah. So if you want to install Anaconda, I think it's a pretty solid. Yeah. Installation of Anaconda, some like kind of how-to on how to move around, and then some installation of common packages that you need. Yeah. So it's not too bad. I feel like it's a pretty good overview. And then one of the things I did was I was chasing around how entropy was calculated. I kind of found some interesting things about how it works. So so when you run entropy in skimage, you have to run the filters. You have to call filters, rank, and then entropy. And this is the documentation on it, or this is the source code. So you see how you give it the image, mask if you want it, and a couple other things. But what happens is when you start chasing around what functions it's calling, I saw that it calls this return to apply scalar per pixel, which is a package that they use to run functions in, kind of like, it seems like it's their internal generic filter maybe. So they run this function and then it calls generic underscore cy.entropy. And someone told me a while back that whenever I see a function with an underscore in the first part of it, it means don't touch it. So you're going, it's like, or like if you put two underscores and two underscores at the end of it, it's kind of like, this is like some interior stuff, like don't mess with it. Because sometimes like if a function's not working right, you can tweak it, what you need. But the stuff with the underscores is like the internal like build and like how it's running. Yeah, like you're gonna break it if you mess with it. Maybe. I don't know, but that's not true. You still want to mess with it, like, but it's just kind of a weird rule of thumb, I guess. So I chased around and I found what that generic.cy does, and it took me to this entropy function right here, where it looks like it's calculating the it maybe is parsing the data, and then it calls this in the core, it calls kernel entropy. I jump over here and you see this kind of interesting looking code. the CDEF, inline, void, kernel, entropy, and then you can see the calculation that's doing. I was going to try and hash out how this was going to work, but I think it's going to take a little bit more time to see what variables are being passed where. But this code, it's a little bit different. It doesn't really look like Python. And I was thinking about it and I realized that I'm not in a Python file anymore. I was in this PYX file, which is called Cython. It's a Cython file. So straight from their website, Cython is Python with C data types. So it's this kind of quirky mix between Python and C/C++. And the code runs really quick. So a lot of people like to implement their Python codes. Like you kind of, one of my old bosses was telling me like what he'll do is he'll type up, like get something working, like an idea that he has for some code, and then he'll convert it into Cython and it runs super, super quick. I watched an old video. I couldn't find the video, but from a while back, I think it runs like, so if like the quickest the code can run is like C/C++, like Cython is like 70% of that, and Python's like far below that. And this kind of breakout shows the simplicity. So Python's obviously more simple. Cython has a pretty wide range. It's some things are simple, other things are pretty complicated. And then C, C++, and Fortran, which is really complicated. But oceanographers and meteorologists that don't know how to code love Fortran because everything runs quick.
Yep.
Yeah. So here I was kind of doing a little bit more reading on it. I think the big thing with it is what makes it so quick is your so with C you tell what data types are and you kind of keeping track of the variables a little bit better. So here you can see like this example function test y = 0 and then it has a for loop and it's adding I every single time to y and then returns y. With the Cython code, this is kind of, I think, on the more basic end of it, but it gets a lot more complicated, like we saw with the entropy functions. The CDEF, I believe, is I think it's a function within Cython that tells it what it is, and then you're telling that it's an int, it's an integer, and then y = 0, and then you have to declare I before you call it in the for loop. So it gets a little quirky, and I think it's definitely one of those things where if you have a really good idea and you want to just speed it up a lot, trying to hash out Cython might speed it up, or like the internal processes. So that's kind of interesting. It seems really complicated, but might be an interesting channel for like that angle, maybe if you want some more, but I'm not too sure how this would be implemented. Yeah, and then real quick, like yesterday, some other things. I emailed the Cube about getting a tornado simulation. They said it's gonna be really crazy till next semester, but they said that they could maybe load it up in their VR goggles. I mentioned to Dr. Pringle, I'm like, well, why don't we just find the files and load it up here? So
Yeah.
Track down who has what, talk to, I know who I would begin with, maybe Dave Carroll, see who has those files.
Bill Carsonson would be your first step, probably.
Okay, I'll talk to Carsonson and see what he has. Because that'd be cool if we can just do it here so we don't have to track them down. I was in that like coding mood where I had like a bunch of cool ideas I just didn't finish. I just like started it and then started another project right after. So I started working on the ND generic and standard deviation, mostly just researching. And then I kind of got distracted and I found the SK image blob detection. So in their, one of the functions that they have in their image detection and kind of like those processes is blobs. And one of the blobs that one of the algorithms you can run to detect blobs. So their example was you're pointing a telescope at the sky and you want to find every single star and highlight it. One of them was Laplacian or Lagrangian of, oh man, I should have wrote this down. The Laplacian of the Lagrange, or LOG is the acronym. I forgot what it stands for, but that loops back to the Kuhner et al. Paper that Dr. Shaw worked on, where they used that filter, the image processing algorithm to get their data ready for their models. So I think I'm gonna work a little bit more on seeing those relationships with those pre-processing algorithms. And then I wanted to come up with an idea to like clip tips, because like if I have too much data and I just want to test things out, I can't be running on these huge data sources. So I was like starting to code up like a Python package that can just, or just a program that could just clip the TIFF and then output it to a folder. And then Jim was bringing up some good points about how it got more complicated, so I just kind of abandoned that after I realized.
Why don't you just section out that piece of the array?
That's true. Yeah, that's a good point. Okay, I'll look into that. Yeah.
I was just trying to go straight from the raster to clipping the raster with Shapely and stuff, and it was kind of hard.
Yeah, especially when you're doing this prototyping, all you're really going to need to do, because all you're really running it on is an array, right? Like you don't really care about the spatial properties except for the cell size.
Yeah.
So the easiest way around it, and in fact, I've got a little bit in mind, you know, like you just want to run it on a little 300 by 300 spot or 1,000 by 1,000. You just, you know, X sub 200 to 1,200, 200 to 1,200, grab a little piece out.
Okay.
That's the fast way to do it.
Okay, that's a good idea. Sounds good. Well, that solves that problem. And then for next week, kind of the same. So some of the goals. I'm still struggling with that OpenCV, so we'll have to put our minds together and figure that out.
Yeah, we'll talk about that today.
I'm gonna read some more papers, and I don't know. That's the overview. Work on some of the filtering algorithms too. That's all I got.
Okay. Sam, yeah, when we talk today, let's talk about the circular standard deviation, and OpenCV. So make sure you're at a point where you can work on your laptop or whatever.
Yep, that sounds good.
Okay.
Perfect.
Alrighty. Anything else from anybody today?
We were just kind of talking about what maybe some more needs for 3D printing wise, about some spools. Maybe.
So yeah, I haven't ordered those 2 yet. Are those still all you need?
Oh, we were a couple rolls of blue, maybe another roll of black. So
Yeah, what we have left is like pink and half a roll of black. So
yeah,
Okay.
not ABS or the copoly or whatever. But
yeah, just among the PLA. We have some.
Okay. What do you want the blue for?
Finish up the this thing I started at the beginning of the semester on to hold the Oculus Rift. There's a couple pieces left that we got that need to get printed, and they're kind of big. So I was either gonna go to the library or print it here, but I wasn't sure
Okay.
yet. So
All right, sounds good.
cool.
1 black, 2 white, 2 blue.
Yeah.
Okay.
Awesome. Thank you.
Thanks.
Sure.
Yeah, have a good one.
Sure. All right. Thanks, everybody. We'll see you later this afternoon for the individual meetings.
See ya.
Bye.
Bye.